Hi everyone and welcome. In today's video, we're going to take a look at another example of computing a limit of right endpoint approximations. So in this example, let A be the area underneath this quadratic over the closed interval from 2 to 4, and we are asked to compute the area as a limit of right endpoint approximations. Now we could also compute this area using a limit of left endpoint approximations or midpoint approximations, since in the previous video we discussed a theorem that said that if you have a continuous function, then all of these limits of approximations approach a single unique number. And if the function is non-negative, then we define that unique number to be the area underneath the curve on this given interval. In the previous video we did do an example, but it was a little bit simpler. This will be a little bit more complicated because we will have square terms and multiple terms involved, and so we will have to use more power sum formulas. And so let's take a look at how to do this example. We begin by collecting all the ingredients. Remember, Rn has a formula. We need like the width of each rectangle, we need f of xi. So the goal of step 0 is to just find these ingredients that we can plug into this formula. The first thing we'll do is we'll take the length of the interval, which is 4 minus 2, and divide it by the number of rectangles. In this case, let n be the number of rectangles. Hence, the width of each rectangle is given by the expression 2 over n. Next, let's compute an expression that represents the right endpoint of each interval. So we start at 2, and we add multiples of the width, and the width is 2 over n. And since we want the right endpoints, we let I run from 1 through n. Next, let's compute the expression for the function value at these right endpoints, because this is what represents the heights. So all we have to do is just take this xi and plug it into the function. And so what we get is this expression. Then we can FOIL this out to get here. And then we can collect all the like terms to get this nice simplified expression for the heights of each rectangle. Great. The next step is to write the right endpoint approximations in terms of power sums. So the formula for the right endpoint approximation is as follows. And now we just plug in the ingredients that we found in step 0. So the width of each rectangle is 2 over n. And then we sum up the function values. And we have an expression for each function value evaluated at the right endpoint. So we plug that over here. It just came from directly here. Now the goal is to distribute this summation as deep as possible and factor out any constants that you can, so that at the end we just get power sums. So in this step, I've simply taken this sum and distributed over each 3 term to get here. And then I just factor out the constant and factor out the n squared here, factor out the 14 and the 2 here, and similarly just brought the 9 out. Because all these numbers are constant with respect to the summation variable is I. I is what is varying. And so we end up with this expression, and we have achieved our goal. We have written the right endpoint approximation in terms of power sums. We have formulas to replace each of these power sums with. In the next step, I have replaced each power sum with its respective formula to get to this next step. Remember that the sum of n ones is just n, so that one is pretty straightforward. And for these two, I had to use the formula that I gave you before. Now I like to rewrite these expressions slightly differently because the goal is to take a limit. And to take a limit at infinity, you basically want to have these 1 over n terms show up. So to that end, we are going to take these 3 n's and distribute them evenly like this. So that's why I've written this. Here we have these 2 n's, so we're going to distribute n over here to get this. And here the n's just cancel, you just get 18. Next, these n's cancel. This n I can distribute to this term and this term. So n divided by n will give me 1, and then I'll get like a 1 over n. Similarly, over here I can distribute the n to each term inside, and I'll get 2 plus 1 over n. And then same idea over here, you can cancel the n's, you can divide each term inside here by n to get 1 plus 1 over n. And this will lead you with this expression. Now we want to FOIL this out to get this expression, and then distribute and collect like terms, and you will get this nice clean expression at the end. The last step is to compute the limit. Therefore, the area is the limit of the right endpoint approximations. We have an expression for this. It's this nice simplified expression. Put that there. And so we're taking the limit as n approaches infinity. As a result, this term will approach 0, and this term will also approach 0. And we're going to be left with this constant. And this constant represents the area underneath that quadratic over the interval 2 to 4, I believe it was. Great, and let's take a look at one last problem. Here we're asked to describe the area represented by this limit. So in previous questions, we were trying to build this limit and then try to simplify and evaluate it. But now we have to reverse engineer and pick out what is our interval, what is our delta x, what is our function, and just describe the area that is represented by this limit. So what we see is that this is our delta x. So delta x is supposed to be 3 over n. As a result, we know that 3 represents the length of the interval. Then I see that this quantity should be my endpoints, xi. And we know the form of xi is that this is our a, and then this is like our I times delta x. And so this is agreeing with what we found over here with our delta x. So that means this must be a. This is the left endpoint of the interval that we're looking at. To find the right endpoint, just take this a value, plug it in here. So if you add 2 on both sides, you get the right endpoint being 5. So b is equal to 5. And lastly, the function under consideration appears to be x raised to the 4th power, because that's where we're plugging in our right endpoints. And so therefore, the final answer is that this limit describes the area between f of x equals x raised to the power of 4 and the x-axis over the closed interval from 2 to 5. Okay, so this is a basic problem, but it's an important skill. You also should be able to identify these limits as limits of Riemann sums and see that it's basically describing the area of some region. And this will always be your delta x. And then over here, you might have some like trigonometric function or some e raised to something, right? That's how you identify the function in question. And then the argument to that function will be like the expression for your endpoints. And so that's how you work backwards in general. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.